All right, hello again. This is probably the final video for torsional stiffness simulation. And if you remember last time where we left off, the simulation was not solving, and I said that I would spend some time and try to debug it as best as I can. And so after going through a little bit of debugging, I have concluded that I think there's just something wrong with the geometry of the this particular model that we're working with. If you remember earlier, we did have some trouble importing or sharing the geometry from this geometry section into the model module. And so the way we resolved that was we just unshared the chassis beams. And this ended up working for our purposes, but again, it wasn't the right way to do it because technically that information of the chassis geometry is not completely shared with the this model module. And so that is most likely what is causing this error. And as I said before, also the sharing issue was not an issue with all the previous geometries that I've set up. And I'll go through after just making a few more comments about this simulation. I'll go through one of the simulations that did end up working, and we'll see how it's different and why that's like the right way. But regardless, all the information that was discussed and shown in this simulation, even though it didn't give results in the end, the entire setup is valid and reproducible. So yeah, all the information is still good. It's just unfortunate that it didn't end up being what I thought it was. And this is my first time solving this particular chassis as well. And so it's just a little unfortunate, but we'll just have to deal with it. I'll continue to debug afterwards, after all these videos are published, and maybe we will get results in the end. But just as a way to conclude the documentation of torsion sims for formula racing at UC Davis within ANSYS with complete geometry of the suspension, or at least a good model of the suspension. Just to complete that documentation, I just thought I'd make some notes on this video and just wrap it up. But yeah, anyways, getting back into it, I'll just show you some of the debugging techniques I did use in case you run into something similar and are wondering, okay, what do I do next? So the biggest thing is when you do try to solve it, you're going to see some errors, some warnings and some errors. In the simulation that did work, we'll also see some of these similar warnings, but no errors because it did solve correctly. Just clicking into these errors, we can see it's saying that the model is under constrained, or there's some contact related issues. And the other error is at certain nodes, it's just not solving correctly in certain directions. So like the way for this particular error, one thing that I did was locate the node that it's talking about, node 897. And I just tried suppressing that that beam and seeing what happened. And this particular node was then good because, you know, it didn't exist, it was suppressed, but the same error came up at a different node on this beam. And so I thought that was really interesting. But yeah, I'll go ahead and show you how you can find out where is node 897. So the easiest way to do that I found is you just create a random name selection. I created it here. And rather than the geometry scoping that we're used to, we're just going to click worksheet. And when we do that, we can just add a node or add a selection in the worksheet. Make sure it's add entity type mesh node, and we're going to define it based on the node ID. Set it equal to 897, which is what the error message gave us. And then when we hit generate, it automatically locates that node and creates a little indicator right there. And so this is just useful seeing, okay, where is this node? And again, the fact that the node is on the chassis tells me that it's probably an issue with the way that we got around the other issue that we found earlier, that I talked about earlier, just with the sharing issue. So yeah, if the node happens to be on one of the joints, then that means, okay, maybe our uh, boundary conditions are off, or there's something wrong with the joint. And so you can go in and troubleshoot that, play around with the degrees of freedom, maybe constrain it more to see if that is the problem, if that makes it solve. That's one technique that I've personally employed with some of the other simulations. Um, Another comment about the messages that the software is giving us. This is an issue that we actually saw when we were having trouble importing the chassis geometry. You might remember seeing this briefly. I don't think I called it out, but it was there. And this is an issue that I haven't been able to figure out which beams have a length of 0, because that just means that the geometry has some really, really small beam that it's ignoring properly, but that just tells me there's something wrong with the geometry. So yeah, that's another indicator of the same point that I made earlier. And this error, or this warning, was not in any of the other chassis that I've simulated either. Other things, this is an interesting one. Sorry, if we go back to messages. So this is saying that 2 or more boundary conditions are sharing a common vertex or something like that. And the cool thing about these messages is some of them you can actually click go to object, and it'll tell you which exactly object within the model, the entire module is causing this warning, or which object is this warning referring to. So when I clicked right click, go to object, then it's telling me, okay, the remote displacement condition that I've applied here is the thing that's violating or causing this warning. And so I noticed that this warning was also present in the other chassis that we simulated. So this isn't the reason that the simulation is not solving, but this does allude to something that I mentioned in, I think, the previous video, where ANSYS doesn't like when there's multiple things going on at a single node. For example, or that's the reason why we moved this push rod to the midpoint of the upright rather than to where it actually is at this node. And that's because otherwise there would be 2 different types of joints at a single node, and that's just something that ANSYS doesn't like working with. So we tried to avoid that as much as possible. So yeah, this is most of the warnings you can typically ignore, but they're really important to make note of, because the warnings can sometimes indicate severe errors that are present, that do lead to the simulation not working. So yeah, that is, to reiterate, like, the warning itself will not cause the simulation to fail, but some of the warnings could actually lead to the errors. So that's why the warnings are useful. But yeah, the fact that the previous simulation with this warning did solve tells me that this isn't the warning that is really causing the simulation to fail. So yeah. And then I also, just to try around, I tried turning inertia relief off and large deflection on to see if that would solve it. That didn't help. So this is just another warning that ANSYS is telling us, hey, there's a lot of deflection. Maybe you want to turn large deflection off. But the large deflection constraint is not compatible with also having inertia relief. So that's another thing to keep in mind. And so yeah, my conclusion for this simulation in its current state is there's something wrong with the chassis geometry, particularly due to the way that we've shared it. And I'm not sure how to best resolve that yet, but I will spend some time looking into that. I may or may not make another video explaining how I fixed it. I don't think it's too important, or I guess it is important. We'll see. But anyways, the joints, this is incredibly useful to go through. This applies to even properly shared chassis, and same with the spring definition, name selection, meshing, all the boundary conditions, and all the geometry preparation that we did in the previous module. So yeah, with that, I think it's a good place to stop with this particular chassis. And now I'm going to show you a chassis that did end up working. And we're just going to go through and notice that everything is set up in the exact same way. But that simulation, for whatever reason, had a geometry that didn't give any errors when importing into the next module. So yeah, let's just go through that quickly. So yeah, this is FE7, the previous year's chassis. Let's go ahead and save this one. Okay, so you can see beautiful check marks for this simulation because everything solved as expected. Just going through the workflow as a way to conclude, put in 4130 steel in engineering data. Then we can go into the geometry. It's going to start up space claim, and then you'll see that the geometry is set up basically identical to the way that we set up FE6. And yeah, I really don't know why FE6's geometry is not behaving as expected. But yeah, so we'll just see that everything that we did learn is applicable. Okay, here it is. Let me just hide this. Okay, so we can see everything looks the same. Let me just hide everything. So the chassis beams, they look exactly how they should. It's all green, all the nodes are shared properly. And then the A-arms, just like that, uprights, and then push rods and rockers. And so you'll see, this is actually the simulation in which I learned that the push rods don't need to be modeled in the front because modeling them as direct acting is just good enough. And so you'll see in the next module that I actually suppressed the push rod and rocker, and it's just a spring, just like we did in FE6 in the previous simulation. But yeah, everything looks normal, pretty much identical to how it should look in FE6. So yeah, that's that. And from there, we can just go into the model, and then we'll see that all the joints are modeled exactly the same as we did. The meshing is also the same. The boundary conditions for the actual like loads and fixtures are also the same. But the only difference is this solves and the previous simulation did not. So yeah, another big difference is in the geometry, we had a folder filled with chassis beams, whereas here we have a shared beams folder. Like it's not a grouped folder that we did manually, like we had in the previous simulation, but this is how it should look when it shares properly. So yeah, that's another big difference. And if we go into connections, you'll see a lot of springs here. That's because I was just playing around with it with different locations and also with or without the push rod and rocker in the front. because if we had the push rod and rocker in the front, then the spring would go at the end of the rocker to the chassis, similar to what it's like in the rear, rather than being direct acting in this way. So yeah, the X's just means I've suppressed some of them, and I'm just keeping the ones that are visible. And the joints we'll see are exactly the same. So all sphericals for the chassis and A-arm pickups, all sphericals for the upper upright and upper A-arms, and then all sphericals for the rocker and push rod connection. And then the ones that we did customize are the bottom, 1 second, let me just reorient it a little. Yes, so spherical here at the bottom, at the front right, bottom lower upright. Then we have only free in the Y direction for rotation in this corner, fixed in this corner, and then free in the Y direction for this corner. So pretty much what we did earlier. And then the last two customizations are freedom in the X for both push rods. And again, here you'll notice that there's some other ones that I didn't talk about, because those are just me playing around with having a push rod and rocker in the front, and these are the conditions for that. It's just suppressed. And you'll notice in the geometry too, those are just suppressed, the front push rods and the front rockers. And a cool thing is that if you suppress the geometry within, like if I suppress it from here, then it also automatically suppresses the joints to which that geometry is related to. That's just something to keep in mind if you want to ever customize stuff like that. So yeah, the name selections look pretty much the same also. And quickly just going through the fixtures, we have no X displacement in the front, both fronts. We have only free rotation in the back here, and completely fixed here. These are the front rockers, which I suppressed because we don't have them. And these are the rear rockers, which are also the same. It's rotation about the midpoint of the rocker, and it's the entire rocker being able to rotate about the Y, this local Y axis, with the local coordinate system, and also translate in the local Z direction. It's the same in this rocker as well. And then finally, it's just a force couple of total 2,000 newtons. So at this and this point. And with that, we solve it, and this is the result. And just some post-processing tips. If you go to the top here, you can change the scale. This is a true scale. And you can simulate, see what it actually looks like. It's kind of cool. I personally like blowing it up to an absurd scale just to see whether the like rockers are behaving properly and other cool things like that. To see if we look into the rear, we can see the rockers are pivoting about the proper axis that we defined, at least apparently, which is nice. And we can see that this corner is indeed completely fixed. This one looks like rotation is, yeah, translation is completely fixed here. So yeah, all the, excuse me, everything that we did define is working properly. So yeah, like this is an example of a simulation that works. Feels really nice when it does work. And now I'll just go through just a quick calculation about how to get an actual torsional stiffness value. And so the very first thing that you want is let's understand what the computation is going to be. So let me just pull up a quick paper and which shows pretty well what we're trying to calculate. All right, so this is the paper. It's on our Google Drive if you're on the team, but it's just analysis of torsional stiffness of a formula student vehicle. And so the calculation that we're interested in is right here in figure 3. And so you'll see that this is a front view of the vehicle. These are the uprights, these are the A-arms. Our simulation is actually more complex because it models the suspension as well. And so what we're doing is we're applying a force couple, 1,000 newtons upwards here, 1,000 newtons downwards here. And yeah, so just in general, the formula that we are using, so torsional stiffness, CT, is T over alpha. And what is T? T is just the torque that is applied, and alpha is the deflection angle. So how do we calculate torque? Well, it's just a moment, basically, a torque about the center of the vehicle. And so we just need to find the moment arm, which is from here to where we're applying it is here. And so for our purposes, the moment arm is 24 inches. So 24 inches to meters is 0.6096 meters. Okay, so it's 0.6096 meters from where we're applying the load to here. And so a question might be on your mind that, okay, we have 0.6096 meters from here to here and from here to here. So is the total that times 2? Well, actually, no, because the way the moments add up, a force at this distance upwards is just, or I guess a torque is just the, okay, well, I think I'm not being clear. I think I'm being confusing, but maybe I can just draw it out. So, okay, if we have a force here and a force here, so what is the sum of the moments about this origin? So it's going to be, let's call this F1, F2, and we'll just call this L, we'll call this L. So the sum of the moments about this point is just using the right-hand rule, saying that this direction is positive. We have F1L plus this side, F, that's not clear, plus F2L. And so the total torque is just L times F1 plus F2. And so another thing that this indicates is if we apply all of the force to just one side, that's the same as applying half of the force on each side as it is. So like the couple would end up being the same, if that makes sense. So, okay, with that, what is the torque for our case? So we have torque is 0.6096 times 2,000 newtons, because there's 1,000 on each side. And that, just with a quick calculator, is 1219.2 Newton meters. And so that's our numerator for this calculation. And the denominator is the angle, which is shown. So, okay, if you zoom into this portion of the chassis, you can see a triangle like this in figure 4. And so we know this distance, which I believe the last time I checked. Actually, let me just double check what this distance is. I guess we can do that together. Just opening up the geometry, we can do a quick measure. But okay, so if we know this distance and this distance, we can find this angle just with a simple arctangent calculation. which I can just show in MS Paint. So just copying this triangle here, we can say that we know the relationship that tangent alpha is equal to U1 plus U2 over L12. And so alpha is arctangent of U1 plus U2 over L12. And this will be our denominator, and that's all we need to solve for. And so, okay, how do we find the numerator and denominator of this arctan calculation? So the denominator is pretty simple. We just have to go back into space claims, pull out the measure tool, and just measure that distance. So this is the front. So these two are very close together. That's 380 millimeters. This is 380 millimeters. So that's, we can just call it 380 millimeters. So L12 is 380 millimeters. And what is this distance, the numerator here, U1 plus U2? Well, if we go back to the figure 3 of this paper, U2 is this displacement, vertical displacement, and this is U1. And so how do we find those values exactly? We can create a deformation probe. So we can right click, go into probe, then deformation. And when that pulls up, we're going to say, I guess we can just redefine one. So we're going to scope it off of geometry. We're going to select these 4 vertices. So they just, on each corner in the front. And we're going to say we want it in the Z direction of the global coordinate system. And then it's just going to give us a max and a min solution. So let me just delete that because I already have it. So this is for these 4 vertices, and this is for these 4 vertices. And so just looking at the max values, we have, so let's see. So U1 is 8.7945, and then U2 with the other deformation probe is 6.2331 millimeters. And so now we know that, okay, the units are the same. We have millimeters, here in the numerator and millimeters here in the denominator. So you don't really need to do any conversions. All we do now is write all of it out. 10 inverse of 8.7945 plus 6.2331 over 380. It's all millimeters over millimeters, which is perfect. And by doing that calculation in degrees, we're going to do 0.7945. We get 2.265 degrees. And finally, torsional stiffness, CT, is T over alpha, which is 1219.2 Newton meters over 2.265 degrees, which gives us a final value of 538.36 Newton meters per degree. And that's our final torsional stiffness value. So I hope that was clear how we got all these values. It's a pretty straightforward calculation. It's not too bad, and especially this paper is pretty useful just to show what's going on. And another thing from this paper that's useful is this is something I've done also, where I just basically put probes at the various nodes along the chassis length. And with that, I was just finding alpha values, so in the same exact way. So these alpha values across the length of the chassis. And what that helps you with is just visualizing, okay, where is the stiffness, where is the chassis stiff, where is it deflecting more? So yeah, that's just a useful thing to do. Just a note, when you're doing that calculation, the L12 distance down here is changing throughout the length of the chassis. So you'll just need to go through and get those different cross-section lengths. But yeah, with that, I think that's a really good place to end the video. I hope you were able to gain a lot from this simulation. Hopefully you're able to get some debugging skills as well for when you do get those inevitable bugs in your simulation. And yeah, I wish you all the best with your torsional stiffness simulations, and please feel free to reach out if you do run into some roadblocks that you might need a second helping hand on. So yeah, thank you very much for your time, and have a great one.